dimensions people I say, what kind of functions? If you can do those, you can do it. Yeah.
Our test is 21, 22, 23, is that?
Yeah. Yeah. And I know what you're thinking. We haven't even started 23 yet. It's real simple. It's got one equation in it.
Okay.
Well, 4 equations. But anyway. Bounce off each other very. They reflect very well. Pun not intended. Because it's mirrors and lenses. And it's not all that. And I'll only catch you up to where we get. Anyway. All right, but anyway, we have this problem. I've got a film. We got a thin film that's got a index of refraction of 1.5, and the film has a thickness. The thickness of the film is L, and light this particular wave. So this is a really thin film. This is a really thin film because the wave is the frequency of the wave. No, it wasn't the frequency. It was the wavelength. Lambda of the light is equal to L over 10. Okay? Now, armed with this, it said, hey, how fast did it go through that thickness? Well, we know this. We know that it goes through there, VT equals L, so T equals L over V. All right? So you plug that into, you punch that into good old master of physics. Goes, no, I told you to put it in terms of F. You fool. And so I said, okay, I can do it in terms of F. Watch this. We know this. Here's the big idea from it. N equals C over V. Whoops. Am I going to have to pull over? No, parents here to say that. You know. Anyway, all right. So we've got N equals C over V, and N times V equals. Tingy, can you hear me yet? No. Tingy, can you hear me? You can hear me now. All right. All right. So NV equals C, and so V equals C over N. Dun, dun, dun. And I know this. I know that C, because here's my original wavelength. That's where I got screwed up. I kept wanting to make that as part of the wavelengths that it's going through the thing. Because here's what happens. When a wave hits a material, its frequency stays the same, but its wavelength changes. Okay? So when its wavelength changes, therefore it gets, since the frequency is constant, the wavelength gets shorter. It bounces, and that makes sense to us because as things bounce in, trying to get through stuff, it crowds. Okay, so that means the wavelength gets shorter. All right, think of it that way. Okay, so where the heck was I? All right, so here we are. So C, so because this is this, then C equals L over 10 times the frequency, which is what Cody kept screaming at me from the back row, going, come on, C equals L 10 over the frequency, and then just solve this and you're on your way. And I was like, okay. All right, so anyway, so here we go. So V equals L over 10 times F over N. It seems hard. It seems like it's long and drawn out, but it's really not all that big a deal. And Ms. Grunschmeister taught me I can just bring this in, tuck it in right there, and I've got this. I've got V equals LF over 15. Because N was equal to 1.5. I'll put that back here in the middle. N is equal to 1.5. There we go. And now, so I've got LF over 15 times T equals L. Aha! Let's just go ahead and cancel those L's right now. That equals 1. And so T equals 15, 1 times 15 over F, which is just 15 over F. Which is what I got before I came to class, but for some reason, I blew a gasket on this part right here, because I thought this part was for the V. I was like, no, then I need the other wavelength, and I didn't know what that was. So I was baffled on something that was pretty straightforward. But the key point to this whole thing, this is a big idea behind chapter what is it, 22? And this is the big idea behind chapter 22. Let's look at a couple of the problems here. Where you've got this, where you've got Snell's law, which is N1 sine theta 1 equals N2 sine theta 2. Now, you all are bright. I've known you all for almost a year now, and you all are bright, capable students, so I know you can do algebra and trig all day long. But what do these numbers mean? That's what we got to think. That's the physics part. Okay. This N1 and sine and theta 1. What are those two physical properties that they're measuring? What's N1? What? All right. N is what?
Refraction index.
Yes, the refraction index. So N1 is the refraction index for what? The incoming ray, right? The medium that it's traveling through. So here I've got like, let's say I've got air up here and I've got water down here. And once you all taught this for like 12 semesters, you'll start to know that air equals N equals 1.00 and water N2 equals 1.33. Okay? Now then, as it comes in, boom. How do we measure the angle? Off the plane or off the normal? Off the normal. Right. Right. You got to measure it off the normal. And that's where I kind of did you dirty. I didn't explain that very well. That's the same way we measure the angle for the flux in a magnetic field. Okay? So a lot of you, that's why you blew it on the test. And that's why it's like, oh. But when 70% of you miss that, or half of you, kind of start to go like this as an instructor. It's like, now wait a minute, they all could have blown it. So what's wrong here? I didn't explain this to you very well that the flux is also measured off the normal. So when they said it was, so when they said that the magnetic field is coming perpendicular out of the ring, that's perfect. Then that's maximum. That's the maximum flux that we can get. Okay. And this is the same type of thing. Measured off the normal, so you get theta 1. So this is, I like to make it theta I. In fact, if I ran the world, I'd say that this was I here. I or 1 is the same. It's the incident ray coming in. All right, and then, okay, we drop our normal on through here. Now then, is this ray going to bend towards or away from the normal? Why? Why is that? Yeah, larger refraction index. Right. Since refraction index is larger, it's going to bend towards the normal like this. Bad drawing. And I usually call that one theta 2, which you can't see at all. Believe it or not, that's a theta 2 right there. Okay? And there you go. That's Snell's law. Now then, here's what happens. Now let me talk about the critical angle. Is this all we have? Hold on a second. Uh-oh. Oh, here we go. All right, let's look at example 22 on page 765. There, beat you to it for one. 765. I can't see. But here we go. All right. Oh, let's do another problem before we get to that here. Come on, man. I thought I had another problem. Oh, yeah. We're going to do this one first, and then let's look at 22.6, and then we'll look at 22.7, and then you all are going to look at 22.8, study for your test. Okay? Because on 22.8, we're talking about reflection, refraction, and dispersion. Reflection, refraction, and dispersion. All right, so here we go. Here goes problem 22.6. Now, it's on 765. Okay, here we go. Now then. Okay, here's what I'm going to do. I've got a here's what I'm looking at. It says, what is the critical angle for light traveling in water and incident on a water-air boundary? All right, so since most of us, unless you've been to like one of those exotic casinos or something like that in Vegas or in Bangkok, where I've been to one, but anyway, never been to Vegas, been to Bangkok. But we usually don't think of people swimming above us, right? You know, some of those hotels and stuff where you got the black, you know, and you can see people sitting there. I don't know what the thrill is of that, but anyway, it's supposed to be something. Anyway, because usually it's Europeans and you really don't want to see them in swimsuits. But anyway, kidding. All right, here we go. Boom, 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 boom. All right, so we're going to have the water down here, but we're going to shoot. We're going to shoot the ray up this way. All right, and what we want to know is now then, since this is 1.33, and this is where the ray's coming from, we're going to draw the arrow like that. So this is where the ray's coming from. This is 1.33. I've got 1.00 right here. Which way is it going to bend? Is it going to bend away from the normal or towards it? Away. It's going to bend further away. Okay? So it's going to look like this. It's going to go boing, like that. And that's why somebody asked me earlier, oh, it's Abigail. She asked me earlier, why does that straw in that cup look like it's bending that way when you said the normal's going to bend? Because we're looking at it in the water and it's coming out. So that's why it's bending away, like it does in the picture in the book. Okay? So anyway, this is my, but what we want to have happen is, we actually want this angle to be the critical angle. Well, this is what we want to be the critical angle, and the critical angle is this. It's what causes this thing to be 90 degrees. In other words, it's going to bend so much that it's going to come up here and boom, it's going to bend at a 90-degree angle, okay, or more, all right, or more. In other words, and now, so any light that's coming along here, any light rays that are coming in an incident right here like this, they're going to actually bend underneath, like that. And so that's what you call internal reflection, all right? In other words, they can't get out. Can't get out. All right, so here we go. So here we go. We've got this. We've got, so what we want to do is we want to figure out what the critical angle is. When theta 2 is equal to 90 degrees. Well, first of all, what's the sine of 90? What's the sine of 90? 1. Sine of 90 is 1. So we've got this. We've got N1 sine of the critical angle coming in is equal to N2 times 1. All right, so the sine of the critical angle then, so if you're ever asked, hey, what's the critical angle? You just go, oh, it's N2 over N1. And in this case, and you can only have a critical angle when this happens. When N2, see, this is my N2 because I'm actually coming from the water to the air. And this is N1. This only happens when N2 is less than N1. Okay? It only happens when you have that situation. N2 is less than N1. Alright? And so the critical angle then, no. Yeah, it's the inverse, not the inverse 1.33, because remember what we've got here. We've got 1, 0, 0 over 1.33. So that actually comes out to be, if you think about it, that 1.33 you can make is 4/3. So you've got 1 over 4/3, which turns out to be what? 3/4. Okay? No, not in this case. Because we start, we're in other words, it's like we're a diver. That's what their example was. We're a diver underneath the water and we're looking up. Okay, so we're in, the medium that we're in, has a bigger than that. Okay? Alright. Okay, so there we go. Alright, and then, Okay. All right. Oh, and so, well, as long as your angle coming in is less than this critical angle, whatever this came out to be, I can't remember what it was. It's 48.8 degrees.
Yeah.
The critical angle equals 48.8 degrees, and so anything coming in here less than 48.8 degrees is going to be internally reflected. Okay, it's not going to get out of the water. It's going to bounce back underneath. All right, so there we go. Now let's look at this problem. Okay. Yeah, this is 22.7. Here's what we've got. We've got the index of refraction of a particular transparent material. Oh, I forgot to show you the cool part. What we're going to be doing here is you've all seen rainbows, right? All seen a rainbow? Okay. Hawaii is notorious for having a lot of rainbows. Okinawa had a lot of rainbows. One, because the air is very humid. When the air is very humid, what does it have in it? Water droplets, right? It's got a bunch of water droplets in there. And here's what happens. It's like a now what's going on with a prism? It's not that the physics behind it is not really all that. It looks cool, but it's really not that complicated. Basically, what's happening with a prism is, I think I might just go ahead and call that up so you can see it. So let's go to the projector. Oh shoot! I accidentally turned it off. All right. Anyway, let's go back to the computer here. Is that flashing yellow now? Now I can't turn it back on, right? What's that? Yeah, I have to override it or something. Well, anyway, it'll cool off here in a second. I'll turn it back on once I find what I'm after anyway. So, I was going to say talk among yourselves, but if you're redundant. All right, okay. All right, now I should be able to turn this back on because it stopped flashing. No! All right. Excuse me. Don't need to step on you here, Tori. Which one do we put? No, this is the one that's actually on. There we go. Yeah, it's green. All right. Physically. That's to keep it from turning off and turning on, which is hard on because of the high resistance to that very bright ball that's very hot. It can melt things, melt your circuitry and stuff like that. So they don't. The fan's not going because it takes a while for the fan. Oh well, the physics of it is pretty intense. But anyway. All right. So here's all this stuff you've already learned. Wow, you learned a lot of stuff. Okay, now internal reflection. That complete internal reflection is also this stuff, this fiber optic cable. This is called cladding, by the way. And back in the early mid-70s, when they figured out how to use this stuff, that was the big revolution in fiber optics. Because before then, all you had to pass along information was good old copper wires or things like that. Okay? And light, as we've seen from its spectrum, has a lot higher frequency than this good old copper. Okay? So, in other words, you can put a lot more information on that. All right, so here we go. Now, here's what I wanted you to see before we went to the next problem. All right, now here's what happens on a prism. You get white light coming in. Now the white light that you see outside, or the white light from a flashlight, has all these colors in there, but we'll get to it in the next chapter after y'all come back and are all rested and rejuvenated from spring break. You'll come back and we will learn about how they have destructive interference. The different wavelengths have. All right, can we hold it down just a little bit, please? Thanks. All right, now, because I'm out of the shadow. All right, now, anyway, we've got these, how the different wavelengths do this destructive interference and constructive interference at certain times. And so, anyway, what the prism does is, in other words, we saw that the frequency of the light will stay the same. The frequency will stay the same, but what changes? The wavelength. And so these different wavelengths have different frequencies. And so here's the normal. And so the largest one, let me see here. All right, so here it comes in, and here it bends away from the normal. And so the one that's got, now this is kind of confusing. I don't really like this too much because then I got the answer wrong. But the one that diffracts the most is going to be the violet one, and it has what? It's got the highest wavelength. Okay? The one that diffracts the most has the highest wavelength. The one that diffracts the least has the smallest wavelength. All right. So your problem here in the index of refraction. So it says here the index of refraction of a particular transparent material is 1.4503, and for the red end, for lambda of the red, and of the visible spectrum, and 1.4698 for the blue end. White light is incident on the prism at an angle of 45 degrees. Inside the prism, the angle of reflection of the red light is, okay, inside the prism, the angle, what did they say? Inside the prism, the angle of refraction of the red light is A, larger, B, smaller than, or C, the same as that of the blue light. All right, so here it comes. The angle of refraction as it's coming in here is going to be what? So it's going to be this angle. Oh, so wait a minute. They drawn this picture wrong. Because don't you think they should have? If this is my normal. Oh wait a second. I'm sorry. Here's my normal line. All right. Okay. I was looking at this as my normal. So I was wrong. So in other words, this bends bigger. So in other words, the longer the wavelength, the less, the higher the, wait a minute. This is a shorter wavelength, higher frequency. Shorter wavelength, higher, so the less the wavelength, the less the angle. All right? So the largest one is right here, which is the red. When I was looking at the book, it made sense because I could see that the normal was here. But boy, they drew this thing coming in like, oh, okay, here's the normal, boom, there we go. Ha! Glad we got through that. Now, so here's what they ask us to do. Here's what they ask us. So that's the first one. The second one is, what is the angular separation of the visible spectrum inside the prism? In other words, they want us to come up with what's the difference in the angle between this blue and the red. All right, so here we go. We can do that. Do that pretty easy. We've got, all right. So, for red is 1.4 what? 503. 1.4503. And for blue, 1.469. All right? The index of refraction is a little bit bigger for the blue. All right. Now then, what they wanted to find was, all right, theta incident, the incident light was coming in at 45 degrees. All right? The incident light was coming in, the white light was coming in at 45 degrees. What they wanted us to do basically was find the difference between theta R minus theta B. Okay? They wanted us to find that. Now, that won't be too hard because what you do is you just do it twice. You just do Snell's law twice. Piece of cake. In other words, angle of incidence coming in, you've got N1 Sine of 45 equals n of r times the sine of theta r. I don't know what that's going to be. We'll figure it out here in a minute. Where n1 is in air, so n1 is just 1.00. And we're coming in here, and so theta r is basically just the inverse sine. Theta r is basically just the inverse sine of n1 over nr times the sine of 45. And if you got a TI-83 or 84 or 89 calculator, you can just kind of do that all in one fell swoop. And you wind up with 29 something. Can't remember. 29.18. Okay? And then you do the same thing for theta b. And what we came up with for theta b, do the same thing. And they had, came up with theta b was to be 28.57. All right, so it's not as big. Let's take the difference between the two. And you get 0.423. Okay? That's the difference between the two. Not much. Half a degree. Less than a half a degree. But enough, because as this, you might be thinking, wow, that's not very much. But it's enough as it travels through the prism. I mean, if anybody's fired on a rifle range or done anything like that, done any weapons firing, well, you get your aim off just a little bit here. Further on down the road, it's going to be way off. All right? And the same thing here. These are little bitty light waves. I mean, we're talking nanometers in length, in wavelength. And so if they go through a prism this thick, that's pretty far. That is what? Maybe 2 centimeters or something like that. That's about 2 centimeters. That's 10 to the negative 2 times 10 to the negative 2 meters. I knew I'd figure that out eventually. 10 to the negative 2 meters. What's a nanometer though? 10 to the negative 9. So you're talking, this is 10 million times greater than that wavelength for that thing. So it's got room to really spread out, all right, compared to itself. It's going, wow, that's 10 million miles across there. That's a long way. Okay? All right. By the minute. By the way, I think a nanometer is how long your hair grows per second. Yeah. It grows 1 nanometer per second. That's how fast you do it. That's one of those little things. And the other thing is, a nanometer is basically Grace, what's her name? She came up with the COBOL language. She's the Navy admiral now. Well, she passed away now, but anyway, she said she just kind of held up a thing of rope, meter long, and said, well, however long it takes light to travel this far, that's going to be a nanosecond. So there it was. It was a nanosecond was born. All right. Okay. All right. Anyway, so that's pretty much it. Now, the tricky thing, what if they told you that green light, theta G, had a wavelength of, say 550 nanometers. Okay? Or lambda G. Say lambda G had a wavelength of 550 nanometers. And it was involved in this nonsense. Could you figure out? Here's what I want you to figure out. Could you figure out the lambda G through the material? Through material? How do you spell material? A-I-S. There you go. All right. Could you figure it out through the material? Probably. All right. Because, or you'd have to do a couple steps. One is you would have to figure out, oh, if you're given that lambda G was this, I wonder if we could figure out its index of refraction. If we were told, that it's, here's what we'd be told. That the difference between theta r, we're told that the difference between theta r and theta g is equal to 0.156 degrees. In other words, they're a lot closer together. Then, given that information, could you find n, the index of refraction for g, for the green light? You have to work it backwards, that's all. And could you find the, then, if you found the index of refraction, you should be able to find the wavelength. I'm sorry, I was thinking you'd do a leap that there was no way you could have done it. All right. Okay. All right, now let's talk, oh my gosh. All right, let's talk about mirrors real quick. Reflection. Reflections of mirrors. Here we go. All right. Okay. Basically, mirrors do this. Mirrors do this. Now, you're going to hear something you're going to see something kind of strange. Have any of you ever stood in front of a concave? Mirror, that's one of those mirrors. It's rounded out and it's punched in. I have no depth perception, so it kept me out of flight school. Anyway, I have no depth perception, so I can't really see it. But people with good depth perception and whose brain works properly, unlike mine, if you're positioned just right in front of a concave mirror, you can actually see an image that's in front. You'll actually see the image in front of the mirror. Here, in a good old plane mirror, where's the image? Always behind the mirror. Okay. And here's what we mean by a virtual image. Okay. Here's what we mean by a virtual image. In other words, our eye comes in. The same rules apply. Index of reflection and refraction and all that stuff. This is coming off the normal here. Angle of incidence equals angle of reflection. But it comes back down, the virtual ray comes back down here, and so we see the image behind. It's kind of apropos that we're looking at mirrors here with Alice in Wonderland now in theaters, but anyway. We're looking at images behind the mirror. It's a virtual image. It's not real. We know what's behind the mirror, a bunch of silver plating of some sort, all right? Or some kind of reflective material. But we actually see the image is actually located there behind the mirror, all right? And with a regular old flat plane mirror, there's only two things you need to know about a flat plane mirror. Besides the fact that if you have two mirrors that are at 90-degree angles, and you're sitting in front of it, you stare straight at it, how many images of yourself do you see? Is that a 90-degree angle? 3, exactly, right, very good. I didn't know that, but anyway, it is 3, all right? Here's my question. Some of you are going, what are you saying? Here's what I was saying. If I have two mirrors like this, at 90 degrees, and I'm sitting here looking at it, that's supposed to be my nose, right? Here's my eyeballs, all right? And I'm sitting there. That's a bizarre looking person, but anyway, you're sitting there looking at it. Here's what you're going to see. You're going to see half yourself over here. You're going to see your image over here, here, and here. You're going to see 1, 2, 3 images. Now, how far away from the mirror are you going to be? Just in a regular mirror. Let's just go with the regular straight mirror, and we're going to start getting our distance of the object. Right here, we got our candle here. How far is this distance of the image going to be if this is 10 centimeters? How far is the distance of the image? 10 centimeters, exactly. It's going to be 10 centimeters. And depending on the kind of mirror that we have, when you are, for mirrors, here's what we've got. The distance of the image, if it's virtual, in other words, if it's behind the mirror, if it's virtual, it's negative. So it's actually negative 10 centimeters. All right, here's our 0 point. It's at negative 10 centimeters. And then, for a mirror equation, for the mirrors, here you go. The magnification magnification is equal to negative di over do. So for a plane mirror, so for a regular plane mirror, in this case, we've got this. We've got negative 10 over 10. And so what's the magnification for a regular plane mirror? 1. Right. You don't, it's not a very good it's not a very good microscope. All right. It just gives you an image of 1. All right. Magnification of 1. All right. Okay. So that's really all you need to know about plane mirrors. All right. Now, when we get to spherical mirrors and things like that, oh, here we go. Oh, I'm sorry. They gave me the image height divided by the height of the object. Well, yeah. You'll see pretty soon that the distance of the image and the height of the image, because of good old similar triangles, and, well, actually not even congruent triangles, that, here's my question. Is this triangle congruent to, in other words, this triangle right here, is that congruent to that triangle? Yeah, so it's the same thing. So those things will work out. All right. Okay, here we go. Spherical mirror. You got to learn the pieces of the spherical mirror. Now then, here's our optic axis, and this is the axis, the line of axis that we draw right through the center of it, like that. Okay, and R is your radius of curvature. Your vertex is located on the mirror, parallel to the radius to the optic axis, or right on the optic axis, and it's a distance of the radius of curvature away, so it's sitting there on the mirror. And this is a concave mirror. If we're over here, what kind of mirror would it be?
Convex.
Convex. There you go. All right. See, isn't this much easier than wires and magnetic fields?
Yeah.
Good old, I told you, take it there, good old simple, discrete geometry class. In fact, I've put forward that we should start teaching physics too from here, so you learn about waves and all that stuff here, and we're going to ease into it. And then we kill you in the springtime with, no, Jeffrey's not done this. All right, okay. All right, now then, a concave mirror. Left focuses incoming parallel rays at the focal point. Okay? All right, so here they come. So here is our focal point. All right? In a convex mirror, focal point is in front of the mirror for concave. What do you think it is for convex? Behind it. And I'll tell you right now, here's your second equation. Like I told you, all right, now this equation's easy. All right? Magnification equation, piece of cake. Here's another hard equation for you. The focal length, F, is equal to the radius of curvature divided by 2. F is equal, and get used to this. It says that F is equal to 2 over R. Okay, capital R, small f, focal length. Okay? F is equal to 2 over R. That's for my hands on this side. Okay, there we go. Now then. Alright, so just by looking at these two pictures, is the focal length positive or negative for a concave mirror? For a concave mirror, the one on the left, would that focal length be positive or negative?
Concave, it's going inwards, it's going to be negative.
So this guy right here, what's that focal length? That's positive, because our object and stuff, this is in the real world. See, notice. Now notice, the lines, the lines of reflection that are coming back here. See, this is where I'm saying, yes.
You mean R over 2? Yeah, you said radius of curvature over 2.
Ah, good, it's wrong. You know what I was thinking of? Because a lot of times, I'm not gonna I'll make an excuse for myself. Here's what I was thinking of. Here's the mirror equation. I was gonna tell it to you. There it is. There's the mirror equation. In other words, here's all chapter 23 is. Here's all it is. Okay? It is just manipulating this equation. Alright? It's just manipulating this equation. 1 over the focal length equals 1 over the distance of the object plus 1 over the distance of the image. That's it. And then you've got the magnification equals the negatives of di over do. There are your two equations for chapter 23. That's it. That's all there is to it. Mirrors are cool. And you can do cool things with them. Okay? And we will finish this up when we come back on